Some really fascinating material you sent over. It's all about string theory,
That's right.
specifically looking at this idea of a cosmic symphony. We're going to try and unpack what your sources say about the universe being made of, well, tiny vibrating strings.
Yeah, that's the mission, to really pull out the core ideas, how things we think are fundamental, like energy, mass, particles, even forces, how they might all just be sort of consequences of how these basic strings vibrate. Like the universe is playing music, in a way.
Okay, let's get into it. So the material starts by setting things up, saying, look, maybe the universe isn't built from point particles, like little dots.
Right, forget the dots.
Instead, it's these tiny one-dimensional things.
Yeah.
Filaments of energy,
Sure.
strings. And it's pitched as, well, a shot at a theory of everything.
And what's really key, right from the start, is this idea of unification. The source really stresses that all the variety we see, all the different particles, the forces, it's not different stuff. It's all just different modes, different vibrations of this one single thing, the string.
That's a huge simplification compared to the standard model, isn't it, with its whole zoo of particles?
Oh, absolutely.
Yeah.
Radically simpler at its foundation.
So the source uses this analogy, which I thought was pretty good, like a violin string.
Mm-hmm.
The note depends on how it vibrates, right? And
Yeah.
the idea here is the same for particles, their identity, their properties.
Uh-huh.
It all comes down to the string's vibration pattern,
Yeah.
its frequency.
Exactly. That's the cosmic symphony idea. The universe's complexity, its richness, it doesn't come from lots of different ingredients.
Okay.
It comes from the almost endless ways these strings can vibrate. The harmonics, you could say. It's all about how it wiggles.
And your source connects this vibration directly to energy and mass. It brings in E's Cauchy and Eoshef,
Look.
Planck's constant.
Yes. And this is where it gets really, really interesting.
How so?
Well, the text explains it pretty clearly. A string vibrating faster, higher frequency. It has more energy.
Yeah.
Simple enough.
Yeah.
But then, because of mass-energy equivalence, MC photon,
Yeah.
that higher energy means more mass.
Okay, so a string vibrating like crazy is a heavy particle, like a top quark.
Yeah, that's the idea.
And one just kind of humming along low frequency is something light, like an electron.
Precisely. And presumably, the lowest possible energy vibration. Well, that would correspond to a massless particle, like a photon, maybe?
Got it.
But it's not just frequency. The source says the strings can vibrate in more complex ways too, like overtones on a guitar string. These are the modes.
And these determine other properties, like charge, spin.
Exactly that. The text states that the way it vibrates, its orientation, the nature of the vibration that translates into things like electric charge and spin, its intrinsic angular momentum.
So hold on. An electron, a photon, a quark. They're all the same fundamental object, a string.
From this perspective, yes. Just vibrating in profoundly different ways.
Yeah.
Playing totally different notes. Think about that one entity appearing as completely different things.
That's quite a concept.
It really is.
Now, the source also says one of the big selling points for string theory is how it seems to naturally unify the fundamental forces.
Right.
Because the force carriers, the particles that transmit forces, are also just specific vibrations.
That's the crucial connection. If matter particles are vibrations, what about the messengers, the force carriers?
Like the photon for electromagnetism.
Exactly. The text suggests the photon is just a string vibrating in one particular way, and the gluons for the strong force, other specific patterns.
Okay, that makes sense within the framework. But gravity, that's always the sticking point, isn't it? Trying to get gravity and quantum mechanics to play nice.
It is. But here's where string theory does something remarkable, according to this source. It doesn't just accommodate gravity. It seems to predict it.
Predict it. How?
The theory naturally includes a specific vibrational mode. And this mode corresponds to a particle that is massless and has a spin of 2.
And those are the properties physicists expect for the graviton, the quantum particle of gravity.
Precisely. And this isn't for any old string. It's specifically a mode of a closed string, one that forms a loop.
So gravity isn't something they bolted on later.
No, not according to this text. It says gravity just emerges. It's an inherent part of the structure. Finding this graviton vibration was apparently a huge moment for the theory.
Wow. Okay. The source also mentions something about the tension in these strings. It's enormous, right? 10 to the 44 newtons.
Unimaginably high tension, yeah. And that's critical.
Why?
The source explains that this huge tension is what forces the strings to be so incredibly small down at the Planck length.
Smaller than anything we can probe.
Exactly. And it also means their vibrational energies, the energy differences between the notes, are enormous.
Ah, so that explains why we don't just see particles getting heavier and heavier indefinitely.
That's part of the explanation, yes. The energy needed to excite those higher mass modes is just astronomical, way beyond our current reach.
Hmm.
And it also offers a potential kind of speculative explanation for why gravity is so weak compared to the other forces.
How does that work?
Well, if gravitons are these closed loops, unlike the open strings maybe associated with other particles and forces, perhaps they aren't confined to our four dimensions.
You mean they could leak into extra dimensions?
That's one idea the source mentions. If they can propagate into extra dimensions, their influence, their strength would be diluted in our familiar space-time, making gravity appear weaker.
Extra dimensions.
Yeah.
Okay, the text definitely goes there. It says the math of string theory doesn't just allow extra dimensions, it actually requires them.
Yes, usually more than the three spatial ones we know. And they're described as compactified.
Meaning curled up, super tiny.
Exactly. Too small for us to perceive directly. But, and this is crucial according to the source, they aren't just some mathematical artifact. Their geometry is fundamental.
How is the geometry fundamental?
Because the specific shape and size of these curled up dimensions directly restricts how the strings inside them can vibrate.
Wait, so the shape of this hidden space, it determines the possible notes the strings can play. Like the shape of a violin body affects its sound.
That's a great way to put it, precisely. The source states that this geometry defines the whole spectrum of particles, the kinds of vibrations allowed, and therefore the nature of the forces in our specific universe.
So different shapes would mean different physics.
Exactly. This leads to the idea of the string theory landscape, this vast space of possible geometries, each corresponding to a potential universe with its own set of physical laws.
Okay, let's recap this deep dive. We looked at your source on the cosmic symphony of string theory. It proposes everything is made of vibrating strings. Different vibrations mean different particles, different masses.
Right, energy, mass, charge, spin, all vibrational properties.
And force carriers, even the elusive graviton for gravity, they also just emerge as specific string vibrations.
Naturally, yeah, not tacked on.
And underpinning all of this is the requirement for extra hidden dimensions whose shape dictates the fundamental rules of the game.
It's an attempt, a really ambitious one, to weave everything together, particles, forces, space-time, into one framework based on vibration. It really is something to think about.
It absolutely is, because if the geometry, the shape of these incredibly tiny hidden dimensions dictates the available notes, and those notes are the particles and forces that make up reality,
then the very nature of our universe, why it is the way it is, could be encoded in the geometry of something we can't even see.
it leaves you with a pretty profound thought, doesn't it? What if the specific laws of physics we observe aren't arbitrary? What if they're a direct consequence of the precise shape of those curled-up dimensions, chosen perhaps from a vast landscape of possibilities?
Definitely something to mull over. Thanks for bringing the source material for us to explore today.